Have you ever stopped to think about the invisible code that makes your coffee maker, well, make coffee? Or the code that runs your car, your thermostat, pretty much everything? Well, that's the ghost in the machine we're talking about today. It's called embedded programming, and we're going to pull back the curtain and see exactly what it is. So, let's start with a little riddle. What on earth does a cutting-edge smart car have in common with, say, your washing machine? I mean, they seem like they're from completely different planets, right? But believe it or not, they share a fundamental secret, a design principle that actually powers most of the tech world around us.
And the answer? They're both what we call embedded systems. You see, an embedded system is basically a mashup of computer hardware and software that's built for one specific job. It's not there to let you browse the web or play games. Nope. Its entire existence is about doing one dedicated task and doing it perfectly.
So here's how we're going to break it all down. First, we'll look at the idea of brains in a box to really get their single-minded purpose. Then, we'll dive into the unique challenges programmers face. We'll explore why a really old language, C, is still the king of this world. After that, we'll see how code actually becomes action. And finally, we'll get to the cool part, flipping the bits.
All right, first up, brains in a box. The best way to think about this is that every single smart device you own has its own tiny, specialized brain, custom built for just one thing. And here's the key difference. Your computer or your phone, those are general-purpose machines. You can be writing an email, streaming a video, and editing a photo all at the same time. But an embedded system, like the one in your microwave, it has a much simpler life. Its one and only job is to heat up your food. That's it. It does that one thing super efficiently, super reliably for its entire lifespan. But, this intense focus comes at a cost. It creates this whole unique set of challenges for the programmers writing the software. They aren't working with the kind of power you have in your laptop. They're stuck working under some really tight real-world constraints. And these are the big ones. We're talking about devices with very little processing power and an incredibly small amount of memory to play with. Power use is a huge deal. I mean, think about anything that runs on a battery. And unlike most software, this code isn't just floating in the cloud. It is physically and intimately tied to the hardware it's controlling. So all those limitations, they totally dictate what kind of programming language you can even use. Your final program has to be tiny, right? It has to fit into that little bit of memory. It needs to be blazing fast because it has to control hardware in real time. You definitely don't want any lag when you hit the brakes in your car. And if you can, you want the code to be portable so you don't have to rewrite everything from scratch for a different chip. So, which language ticks all these very demanding boxes? Well, the answer might actually surprise you. It's time to talk about why we still use a language that's been around for over 50 years. C.
That's right. In this world of new, shiny, modern languages, the old-school veteran, C, is still the undisputed champ in the embedded world. And that's not because everyone's stuck in the past. It's a very practical choice, simply because C is almost perfectly built for this job.
So, why C? Well, for starters, it's pretty simple, and the programs it creates are small and super efficient, which is exactly what we need. The tools that translate the code, called compilers, exist for pretty much every processor you can imagine. But really, its secret weapon is this. It gives you the raw, direct hardware control of a low-level language like assembly, but with the readability and features of a high-level language. It's truly the best of both worlds. Now, to get a little more specific, what developers are often using is something called embedded C. It's not a whole new language. Just think of it like regular C, but with a few extra tools in the toolbox. Specialized tools designed to give programmers even more direct, hands-on access to the hardware. Okay, so we've got our language. But how does a line of text that a person types actually make a physical machine do something? Let's follow the journey of a piece of code, from the programmer's screen right into the guts of the processor. It's really a three-step transformation. First, the programmer writes a line of embedded C, which, we can kind of read. Then, a compiler translates that into something called assembly language, which is a lot closer to what the hardware understands. And finally, that assembly code gets turned into raw machine code, just numbers really, which is the only language the processor actually speaks. And that brings us to the coolest part, in my opinion, flipping the bits. This is where the magic happens. We're going to see exactly how a single line of code can reach into the hardware and physically change something, like turning a tiny light on or off. Okay, so inside a processor, you've got these little things called registers. Think of them like a tiny control panel with a row of switches. These switches are called bits. Now, the problem is, if you have 8 switches controlling 8 different things and you only want to flip one of them, you can't just slap a whole new setting on the panel. You'd mess up the other 7. And that's where this quote comes in. To avoid that disaster, programmers use a really clever trick called bit masking.
Let's make this super clear. Imagine this is our register, our little control panel. Each bit is wired up to one of 8 LEDs. A 1 means the light is on, and a 0 means it's off. So as you can see right now, LEDs 7, 6, and 5 are all turned on.
Now, our mission is to turn on LED number 2, but, and this is key, without messing with any of the others. To do that, we use this little line of code. The best way to think about it is like using a stencil. The code creates a stencil that only has a hole over the second position. The special equals operator then merges that stencil with what's already there. So any light that was on stays on, and the new light gets turned on through that single hole in our stencil.
And boom, take a look. LED 2 is now on, and all the other LEDs are exactly as they were before. That's the kind of surgical precision we're talking about.
Okay, but what about turning a light off? Let's say we want to turn off LED number 6. For this, we need a slightly different tool. We use a bitwise and not operation. This time, think of the mask not as a stencil, but as a piece of tape. The code creates a mask that carefully places a piece of tape over just the one we want to turn off, leaving all the others exposed so they stay exactly as they are. And there you have it. LED 6 is now off, and every other bit is untouched. This is what's happening at its very core, millions of times a second, inside all of your devices. It's the essence of low-level hardware control.
And of course, this is for way more than just blinking lights. Programmers use this exact same technique to read what's happening in the outside world. A line of code just like this one can be used to constantly check one specific bit to see if a button has been pressed, letting the device actually react to you.
So there we have it. We've gone from a simple washing machine all the way down to the individual bits getting flipped inside a processor. The next time you press a button on anything, really, you'll know that there's a tiny, dedicated brain inside, waiting and watching, using code just like this to feel your touch. Now that you've actually seen the ghost in the machine, can you ever look at your smart devices the same way again?